Hello, I'm Paul Richmond. I run the Research Software Engineering Group at Sheffield. As well as doing that, I also developed a piece of software called Flame GPU. So this is supported by my EPSRC Research Software Engineering Fellowship, and I'm going to talk a little bit about it today, which is rare because normally I'm talking about research software engineering rather than my own software. Let's see. Okay, so there are kind of two components to introducing this then. So there's the idea of agent-based modeling. So agent-based modeling is a modeling technique for modeling complex systems. So a complex system is a system where you've got potentially lots of interacting parts and some form of emergent behavior. So it's emergent in the, the behavior that we observe can't necessarily be very easily predicted by the small parts that make it up. There are examples of complex systems everywhere, whether it be neurons in the brain interacting and producing intelligent behavior, whether it be the dynamics of crowds, whether it be cells producing complex biological behavior. But agent-based modeling is an approach to modeling these types of systems that takes a kind of a bottom-up approach. So you model the individuals, you model their interactions, and then you simulate and observe the emergent behavior. So it's very different to kind of top-down system-level modeling, but it presents a computational challenge. So having lots of agents, lots of individuals, whatever they may be, each of those has to be simulated independently. And likewise, there's large memory requirements for having lots of communication as well. So the second component then is GPUs. So GPUs are really like an extreme example of a multi-core design. There are many core design. They basically use the same silicon as a CPU, use the same manufacturing processes, more or less. But they're designed in a different way. So they spend more of the die space for GPUs dedicated to compute. And of course, that comes with a cost though. So the trade-off is some of the intelligence in the design that's being added to CPUs to reduce latency. Yeah, so the way I quite often describe the differences is to use a kind of a simple analogy of a CPU is designed for very low latency. So it's a little bit like a motorbike. It's good at doing kind of single tasks very, very quickly. GPUs, however, are high throughput, so there's much more space dedicated to compute and the high throughput because we can process kind of lots and lots of data. So depending on what the task is that you want to do, maybe a CPU is good for you or maybe a GPU is good for you. If you want to move a lot of people from A to B, which is quite often the case within high performance computing, then a GPU is a much better choice than a CPU, which needs to go backwards and forwards lots and lots of times. So the obvious question then is, GPUs are this many core design, lots and lots of cores. So surely if we have lots and lots of cores, surely my multi-agent simulations can run n times faster if I've got n GPU cores. Well, wouldn't that be nice? But unfortunately, it's not the case. So although GPUs have got lots and lots of cores, they work in a data parallel way. And agents, although are individual and could be simulated individually, they do lots of things that mean that they're not completely independent. So for example, they communicate with each other. This is the complex side of the complex system. There's no unified parallel model for an agent. So lots of people do agent-based models that are inherently serial in their design. So transferring that to a parallel architecture is quite difficult. They do all kinds of annoying things like a born and die. They don't stay still, they move around. And likewise, GPU programming is really hard. So some of the benefits that are gained by spending that die space on kind of raw compute means that you need more intelligent programming to utilize them effectively. So it means that GPU programming is hard, and it's not necessarily something that should be encouraged by someone who wants to write a simple agent-based model. So this is what Flame GPU and particularly Flame GPU2 do. So the reason there's this little post-it note is Flame GPU2 is so new that we haven't even got a proper logo for it yet. So it's not quite in beta release. It's been used on a number of projects. We've run some tutorials on it, but it's more or less due to be released as soon as I've got my teaching underway in the next couple of weeks. It's been funded by my RSC fellowship, and it's taken what was an initial piece of software, Flame GPU, and tried to add a lot more flexibility to it. fundamentally, the concepts behind both are exactly the same. The idea is to abstract the complexity of GPUs away from the modelers. Yeah, so just in the same way that machine learning has made GPUs available to researchers without having to understand what a GPU is and does and how it operates, Flame GPUs is exactly the same for complex systems simulation. One of the nice benefits is that with Flame GPU, you can describe your model completely separately from your implementation. So this is vitally important for reducing bugs and improving reproducibility. So the actual behaviors, the core to the way agents interact is kind of hidden behind a library. So one of the other nice things that we've done with Flame GPU2 is add Python bindings to it. Potentially we can do this now with other high level languages, but it makes it much more accessible. It means that you can drive simulations from things like scikit-learn if you're wanting to do parameter exploration. So the way that Flame works then is using this kind of nice mathematical formal model of an agent. And there's a lovely complex definition for it, but actually it's really, really simple conceptually. So basically an agent exists in a state and it performs a particular behavior that moves it into another state. When it performs a behavior, it can either read or transmit messages. Because we have this kind of state-based representation in which things transition from states and utilize messages, it gives us a natural way to parallelize the model. So the diagram on the right is pretty typical of a very large class of agent-based models. So something like a flocking simulation would look exactly like this. And we have three behaviors that are represented by the square boxes. First of all, agents will send some information. So they will send perhaps their position and velocity via a location message. Then agents separately will read those messages in. They don't directly interact with any other agent. They do so indirectly through messages. They read all of those messages in, apply some function to messages that are within a spatial distance that are relevant to them, and then they perform some movement by adjusting their velocity and position. This state-based representation is vital because it means that we can build much more complex models. So here, for example, is a complex model. Imagine trying to implement this as GPU code without having this kind of clear separation. I think this is actually an economy model, but we have even more complicated models than this that are looking at things like TB simulation within the immune system. So Flame 1 worked in this way of describing your model using an XML file and then having some C scripts, and there was lots of complex template processing that would eventually generate simulation code. This was a necessity at the time, but we've done away with that now and massively simplified things with Flame GPU2. So it's all C++ based and API based. So you can still write your model description using XML if you wish, or you can have a one-to-one mapping between kind of what was the XML description of an agent and the kind of model API objects. You simply link with the Flame GPU2 library and you can generate simulations that are either kind of non-visual or visual. So there's relatively simple kind of API objects. You have a model and a population. Your model has messages and agents and environments, and layers determine the diagram that you saw in terms of the execution of agent functions. The types of things that you can do with it then are very, very varied. So it's not domain specific. Here is what we call our kind of circles benchmark model. So this represents that model that we saw visually, that three function model, where we have transmit location, receive location, and move. So this is a very simple model where an agent simply has an attractive force and a repulsive force to other agents. And this is the emergent behavior that we see as a result. So they form these spheres because that's the most kind of compact shape that they can, which balances the two forces. And then because of the distance range that they have, it means that we get kind of clusters of these things kind of merging together. So some of the other application areas have been in pedestrian simulation. So this is quite an old image now, but I tend to use it because it looks very nice. So this is showing the London Olympic Village with about 65,000 people kind of moving between the various locations. More recently, we've been looking at simulations of rail and transport. So this is a transport simulation demonstrating the impact of GPUs versus multi-core on compared to some of the commercial tools that are out there for doing transport related simulations. And finally, two very recent projects that we're working on. So one is the Primage project, which is looking at simulation of neuroblastoma. So this is a form of tumor cancer. And similarly, this is being used in a project called Strichivad for doing TB modeling. And on the bottom, you can see a simulation that we've been applying our pedestrian models and accurate collision detection models to alighting and disembarking of rail during kind of social distancing. So just to quickly summarize, Flame GPU2 provides kind of GPU performance for agent-based simulations. You'll have noted that I haven't presented any kind of performance figures, and the reason being is it's very difficult to do so. It's very unfair to compare Flame with CPU-based products because it's kind of apples versus oranges. What we do have is Python bindings that make it easy to integrate Flame GPU with existing code, application areas in lots of different domains. The team at Sheffield, the RSE team, have got somewhat of a specialism around applying Flame GPU. So we have a number of projects in which we have RSE collaborators that have been developing the next sets of functionality that have been embedded within that. So that's big thanks to kind of Rob and Pete, Matt, Twin and John who've been working on those. Bede comes into this then in that it's going to provide us kind of a new capability. So where we would like to get with some of those particularly biology-based models is simulation of 1 billion agents. So it doesn't necessarily mean a single system with 1 billion agents. That might mean ensembles of simulations which are going to be used for things like parameter search. Ideally, we'd like to do both. So doing whole tumor modeling, for example. The software is available for free. It's on GitHub. Download it, get in touch if you'd like to find out more. If you'd like to do a tutorial on it, then I can provide some free cloud credits if you get in touch. So that is everything. Thank you.